just like we said, for anyone who's recently come into the chat, we're going to do a problem in today's lecture. So if you go to my courses, it's okay. We'll give all the information in the lecture. So if you don't want to look at this now, you don't have to. But if you do want to download or look at the problem we're going to do, if you go under course content for week 2, you'll see here there are the videos to the lectures. But you can also click on this first law starter sheet for lecture 5. So if you click on that, you'll get this PDF. And this PDF is the problem that we'll do in class today. Before we start, does anyone have questions about sort of, I guess, the quiz and the homework that will be due this evening?
Yeah, I had a question about the graphs. When it said PV equals constant, would the graph be a straight line?
Yeah, so here, let me bring this back up here. Did I close this? Oh, you know what? Let's try this. So here, oh, of course, this is going to be right. So here, if you had a PV diagram, right? So you'd have pressure this way, volume this way. So if P times V was constant, so PV is constant. That's a little bit of a tricky one to draw, right? So if pressure times volume is constant, so let's say we were here, right? And this was, pressure was 1 and volume was 1. So now if my volume goes to 2, right? So this 1 times 1 is 1, right? So 2, this has got to be 1/2. Right? And then, so I think that line is going to look something like this. I'm not exactly sure the shape of the curve, but it will definitely decrease like that. Right? So your first impression might be to draw a P as constant curve, right? So I'm sharing my screen, right? You can see this as I do this?
Yeah.
Okay, that's good, right? So you might be first inclined to think of PV as constant, the same as P is equal to constant, right? And that line would just look like this, right? If pressure was some constant. But if PV is constant, you're going to get a curve that looks like this. You could graph it in something like Excel. So if PV is a constant, then P is going to be equal to C over V. Correct? So you can fill in any number for this constant, right? Let's say 1, right? Then you're going to have P is equal to 1 over V. And then you could graph that function. Does that make sense?
Yeah, that makes sense.
Any other questions?
I have one more question.
Sure.
Do you know when you're going to have your office hours?
No, I hadn't posted them yet. So I was thinking that because homework is due on Mondays typically, right? So I was going to have my office hours probably I was going to have one office hour right before class on Monday. So maybe from 3 to 4. And then I do want to have another office hour time in the mornings because I want to make sure that everyone can attend at least one of the office hours. So I was still looking for another time, potentially like 10 or 11 o'clock sometime during the week. I'm also happy to, if someone has questions about the homework today, I'm happy to stick around after the lecture and we can talk about that as well. Does that sound good? Okay, so as you hopefully know, right, so we have quizzes that are typically due on Sunday, but because of Memorial Day, I bumped that to being due today at midnight, whatever your time is. These should all both say 23:59, right? And then homework, which is usually due on Monday, will be due today also at 11:59 p.m. So for the quizzes, you go into My Courses and you complete the quiz, right? So you go into quizzes and you should be able to see quiz 1 and you can complete it. For the homework, what you'll do is on whatever kind of paper you want, when you do your homework problems, then you can scan them, maybe in something like Cam Scanner. Cam Scanner will let you take multiple images of things on your phone and combine them into one PDF. So I find that's at least one way of doing it that's pretty useful. So you're welcome to do that and then submit your homework as a single document or a single PDF. So the good news is the quiz, we had 8 of 14 people had completed this by 2:45 today. And then the homework, I think we maybe only had one person completed, but I would imagine that will be done, by the end of today. So hopefully everybody gets a chance to work on that and submit it by the end of the day today. Like I said, in class today, we're going to be working on a problem that does the first law. So if you want to go to My Courses and then to Content, if you look under week 2, you'll see this, and there's a first law starter sheet for lecture 5. If you click that, then you'll get this page. It's a 2-page document that goes over, that gives you kind of the given information for the problem that we're going to do today. So going through this, typically this will happen in class. So before you come to class, if you look for these starter sheets that are associated with whatever lecture that we're working on, you should be able to bring that paper with you. Normally in class I would hand out a sheet, but obviously that's not possible now. But if not, I'll give the given information throughout the lecture as well. So if you don't want to sort of go to this and download it or print it out, that's okay too. So up until this point, we've been talking about the universe, right? And we break the universe into 2 pieces, the system and the surroundings. We look at how the energy in the system changes over time, and we know that change in energy has to be due to heat that gets transferred into the system and work that gets transferred out of the system. So when we're working on these first law problems in thermo, first thing we got to ask ourselves is what's in our system. So the answer could be water, maybe it's liquid water, maybe it's steam, maybe it's some combination of the two, or it could be something like an ideal gas, like air, right? And then we're going to ask ourselves, is the system open or closed? And that means, can mass come in and out of the system? And for the first portion of the class, up until about the first midterm, we're only going to be thinking about closed systems. And then we want to know what happens to the system. How do we describe the process that the system undergoes to go from this initial state to this final state? And that process will be some combination of heat and work. We know this because it's described by the first law. The first law tells us the change in total energy in the system is equal to the heat in minus the work out. So this lecture is about the first law of thermodynamics. So we know that for closed systems, there's no transfer of mass across the boundary. So we talked about we can have something like this. So here our control system is this box in here. So it's the gas that's in this piston cylinder assembly. Now the piston might move up and the piston might move down, but as long as these valves up here are closed, then there's no mass transferring in and out. So it's the same air that's in there, it's just being compressed or it's expanding. So there's 2 different kinds of closed systems. Usually we will talk about a normal closed system where there's no mass transfer, but we can transfer either work or heat. In some special cases, we'll be talking about isolated systems. Isolated systems do not interact with their surroundings in any way. So that means that there's no heat transfer and no mass transfer with the surroundings. So things can happen inside the system, but there's no communication between the system and the surroundings. So then what's the first law of thermodynamics, right? It's got this big important name, right? Like it sounds really important, really grandiose. And it is, because it's one of the main tools that we use to try to understand what happens in the universe. So the first law is conservation of energy. It means that, so my internet's not been great. I actually tried to time. I don't know if there's anything I can do for the. Is it the audio or the video that's poor? I think I'll try to go to the router settings, see if I can prioritize my computer here. But other than that, I'm not sure that I can do much. So hopefully that works out a little bit better. We will try to move forward here. So we know that the first law is conservation of energy, that energy can't be created or destroyed, but it can move between the system and the surroundings. We talked about this long verbal definition before, but I don't like to read this whole thing because it's pretty long. So instead, I like to describe the first law with mathematics. And what it tells us is that the change in energy in my system happens because of heat transfer in and work that's being done from the system on the surroundings. So when I look at this equation, I can look at the left-hand side here and see that there's this change in total energy between two states. And typically when we talk about closed systems, we're talking about changes in time. So the subscripts 2 and 1 both refer to instants in time, where state 2 comes after state 1. So this energy, like we talked about last class, is a summation of lots of different kinds of energy. Kinetic energy, potential energy, spring energy, and this internal energy, which is this new kind of energy that we learned about, U. We know that Q is heat transferred into the system, and work is heat transferred out, or is work transferred out of the system, or work done by the system on the surroundings. And we remember that with this kind of mnemonic device that tells us hip to win, or heat in is positive and work in is negative. So the first law is important because it helps us understand what's going on in the world around us. In this class, which is a class really about conservation of energy, you'll use the first law in basically every problem that you do. You'll use it in several different forms, the first of which is on closed systems like we see here. But even when we start to go to open systems and we allow mass to move in and out of our system, the concept is still the same, that we're going to conserve energy. So for closed systems and closed systems only, we're going to use this equation. We know how to find work. If we have a relationship between P and V, then we can find work as the area under this curve on a PV diagram, because we know that work is equal to the integral of P dV. Typically, we have a polytropic process where PV to the power of n is equal to some constant. So now we have different values of n, whereas if n is equal to 0, we have an isobaric process, meaning that the pressure is constant. If n is equal to 1, we have an isothermal process, where the temperature is constant. If Cp over Cv is, if n is equal to Cp over Cv, that tells us that the process is adiabatic. That's one of those fancy engineering words. It means that the heat transfer between the system and the surroundings is 0, so that our system is well insulated. And if n is less than 1, Q is very high relative to work. So there's different physical interpretations of the different versions of this equation that we can come across. So we know how to find work. It's the integral of PdV. Typically, we're going to then want to find what delta E is. So E2 minus E1, we know that this is delta E, and that delta E is a sum of the change in all these different kinds of energy. Kinetic energy, potential energy, spring energy, and this new kind of energy, internal energy. So we can think of this equation, if we sub this in, as the change in kinetic energy plus the change in potential energy plus the change in spring energy plus the change in internal energy is equal to Q minus W. Now you might look at this and get a little bit frustrated because there's a lot of terms here. So Well, the reason that we split it up like this is because typically in the problems we're going to do in this class, the change in internal energy is much bigger than all these other energy changes. So we'll often be able to neglect the change in kinetic energy, potential energy, and spring energy. And our closed version of the first law will be U2 minus U1 is equal to Q minus W. So then we know that work is the integral of P dV. We can calculate delta big U, the change in internal energy, as the mass times the change in the specific internal energy. We don't know how to find specific internal energy yet, but we're going to start looking at that next class, which will be tomorrow. So usually, to do a first law problem in this class for closed systems, we'll figure out what the relationship of P is with respect to volume and find the work. Then we'll work on fixing states, and we'll find the change in specific internal energy and multiply that by the mass. And then we'll use the fact that we know W and that we know delta U to find the heat transfer. So that's the end of the kind of new material, which is even a little bit of review. And after that, now I want to go into this problem. But before we get to there, I guess there's two things. So first, has the audio quality still been spotty? And second, do you have questions about how to sort of approach these first law problems? Can anyone hear me? I don't see any responses in the chat. So I'm hoping, I guess I'm checking my email now just to make sure that that there's no sort of slew of emails saying that no one can hear me. Can anyone hear me?
The audio is still a little spotty.
All right. Well, we will. I guess that's unfortunate. Like I said, we're working on trying to update our internet connection. So we're going to try to go through this problem. I will post the video of this, and then I also have sort of the canned version of the lecture, but I'll post this as we do it, and then hopefully it's at least usable that way if you're not able to kind of hear as we're going through in real time. So in this problem, we're told that a gas in a piston cylinder assembly is compressed from P1 at 3.4 bar at a volume that's given to P2 at 8.2 bar in a process for which the relationship between pressure and volume is given. PV to the 1.2 is constant. The mass of the gas is 0.183 kilograms. During the process, the heat transfer from the gas is 2.2 kilojoules. Determine the change in the specific internal energy of the gas in kilojoules per kilogram. We can neglect kinetic and potential energy effects. So we'll try to do this problem together. So on the problem sheet, if you had a chance to look at it, we're given this picture. So this picture tells us what's going on. It tells us that the volume is getting smaller, and as the volume gets smaller, then our pressure gets larger. So if we're on this PV diagram, this is our state 1, and then as we shrink the volume, the pressure goes up because this is a closed system. So now we're asked what the total amount of we're asked what the change in the internal energy is, right? So we know that this is a first law problem. So if we've already assumed that the change in kinetic, potential, and spring energies are small relative to the change in internal energy, then we get this equation that U2 minus U1 is equal to Q minus W. Now I've told you that what we're going to try to do generally in these problems is first find work, then we'll usually try to find delta U, and then we'll use those pieces of information to find Q. But we don't know how to find delta U yet. So actually in this problem, we're going to do this a little bit differently, where we're told Q, we'll find U, and then we'll go back, or we'll find W, and then we'll go back and use that to find the change in the internal energy. So we're required to find I guess ultimately we're required to find the heat. No, we're trying to find delta U, right? So here I'm going to try to do this with this pen here instead of animating through on the slides. So if you prefer the animations on the slides, the video that I've recorded and already posted on my courses, we go through the slides version of this. So here I'll try to write this out like I was writing it out on the board. So the first thing that we'd want to do is we want to look for the known information. Oops. So the first thing we see here is that we're given pressure 1. So this is P1 is equal to, it says 3.4 bar, but I prefer to have my pressures in either pascals or kilopascals. So I'm going to multiply this by 100. So this is 340 kilopascals. Right? I'm going to do the same thing over here to P2. This is going to be 820 kilopascals. We know V1, right? We're also told that this process happens in a way that P times V to the 1.2 is constant. We're told the mass in the system. And we're told the heat transfer. So this is a little bit tricky because we know that the magnitude of Q is 2.2 kilojoules. Now, does anybody want to guess what the sign of the heat transfer is?
Positive.
So why do you think it's positive?
Hip to win.
Right? So we know that heat in is positive, right, from the mnemonic device, right? And this is heat transfer from, so this is heat transfer from the gas. So this is, if I was drawing my system here, right, here's my system. You're going to have to excuse my drawing. Learning how to use this electronic pen, right? So if this is my piston and it's moving in, right? What this tells me is that heat transfer from the gas. So the gas is my system. So if I drew a control volume here, so heat is being transferred from my system to my surroundings. So heat in is positive, which means that heat out must be negative.
It's negative.
Right? So this is one of the things that's pretty tricky. So if you ever go, you're working at a co-op job or something, or you're an engineer after you've graduated, no one that you talk to is going to say, oh, this process has negative 2.2 kilojoules of heat. Right? You're going to have to think about how that sign works. Right? So here, I think we've got all of the known information, and we also know here that we're trying to find, we want to find the change in delta little u. We don't know what that is, but we know that it's in kilojoules per kilogram. Does that make sense? Do people have questions about sort of how we took this information from the problem? So we know that our governing equation is given here, right? So here we can simplify this a little bit. We can make this, oops, I have to apparently select the pen again. So we can make this, on the left-hand side is the mass times little u2 minus little u1 is equal to Q minus W. Right? The good news here is that we know Q. Right? So Q is equal to, what did we say? Negative 2.2 kilojoules, I believe. Right? So we're trying to find, we also know, it told that the problem told us the mass, right? So here we don't know delta U, but that's okay because that's what we're trying to find. So ultimately we would like to find this. And if I knew the work, then I would be able to find delta U. Does that make sense? And we know from the lectures that if we go the integral from v1 to v2 of p dv, then that's going to be equal to the work. Does anyone have questions about how we're setting the problem up? So now we're going to try to find the work. Right? So here we know that work, oops, let's do this in blue. We know that work is the integral of p dv from v1 to v2. Right? And then the problem also tells us that p v to the power of 1.2 is some constant. But what I really want here is p as a function of v. So that's going to be equal to my constant times v to the negative 1.2. So here to get this, I divided both the left and right hand sides of my equation by v to the 1.2. So if I put that back into my integral, I can take the constant out. So this is going to be some constant from v1 to v2 of v to the negative, oops, to the negative 1.2 dv. So to integrate this, so first I take c, I'm going to divide by negative 0.2, and then this is going to be v to the negative 0.2 from v1 to v2. I can evaluate this, so then I would get c over negative 0.2. This is going to be v2 to the negative 0.2 minus v1 to the negative 0.2. So now you might feel that this starts to get a little bit tricky. This is where there's a little bit of sleight of hand in this particular question. So we remember that PV to the 1.2 is equal to a constant. So that means that this constant is true if this is P1V1 to the 1.2, but it's also true if this is P2V2 to the 1.2. So the constant has different values, right? And I can use that to my advantage when I start to multiply this back out. So here, if I redo this, I can say that 1 over negative 0.2 times c over v2 to the 0.2. So now all I did was, instead of calling this v to the negative 0.2, I just said 1 over v to the 0.2, right? Minus c v1 to the 0.2. But now I've got two different values for c. So over here, I'm going to say that c is going to be p2 v2 to the 1.2. And over here, I'm going to say that it's p1 v1 to the 1.2. Both of these are true, but by using the different expressions here, I can get rid of the, like I can simplify the volume terms. So this is going to be 1 divided by negative 0.2 is equal to, so here's kind of the beauty, is this becomes p2 v2 minus p1 v1. And now if you don't like a negative out here, we can multiply this whole thing by negative 1. So this becomes negative 1 over 0.2. Now I'm just going to flip these two terms around if the signs change. So this is going to be p1 v1 minus p2 v2. Does that part make sense? So now we have an expression for work. So here I can go, this is going to be equal to, so first I know that this delta U is M, which I know, times U2 minus U1. My Q is negative 2.2 kilojoules. And my work is going to be 1 divided by 0.2 P1 V1 minus P2 V2. So I like to work this all out symbolically because it helps me to figure out what I know and what I don't know. So here, I know the mass, right? Q, I know. I actually wrote the words in here. But I know P1 and V1. I know P2, but I don't know V2, I think. I think that's true in the problem. Let's check. If we come down here, we're told P1, so we're told P1 and V1. We're told P2, but we don't know V2. Right? So here we don't know V2, but we know that P1 V1 to the 1.2 is equal to P2 V2 to the 1.2. So here I can isolate for V2. V2 to the power of 1.2 is equal to P1 over P2 multiplied by V1 to the 1.2. So from here, I can figure out, or if I want, I can get rid of this part over here and take all of this to the power of 1 over 1.2. So now I can find V2. So symbolically, I know everything. So now it's just a matter of putting the math in. So maybe before I show you, I'll go back to the slides to show you the numerical answers. Does anyone have any questions about sort of the derivation of the symbolic solution that we just did?
Yeah, for that exponents, can you go back to the last slide? Yeah, when you divide, oh, never mind. That makes sense. I got confused.
Sorry, I did skip a step. So as I go from here to here, was that your question?
Yeah, that was my question, but I figured it out.
Cool. Yeah, it's tricky. I find, whenever I go back, I went back to do this problem today, and the thing that I was like, oh, how do I do calculus again? right? I know I got to add 1 to the exponent, and then I think I'm supposed to divide by something, right? So I had to look that up too. So it's been a while since I've done some math. So if you do think I made a mistake, don't ever hesitate to let me know, because it's certainly possible that I make clerical errors when I'm up here doing stuff. This joke doesn't really work anymore, but I had a speaker. She came in. She's a really, really accomplished researcher from University of Kentucky, and she was saying that when she teaches at the front, she feels like that 3 feet in front of the board is like the zone of stupid, right? So it's really easy when we're up there and we're kind of working on the board and stuff. Really, really easy for us to make mistakes. So yeah, and here I'm thinking about how to use this pen too. So if I make a mistake, please let me know.
I actually have another quick question. Yep. Is it common in these problems that it works out so that it's 1 over some value is equal to P2 V2 minus P1 V1?
This is an excellent point. Every time when the exponent is not 1, you will get to this equation. So you'll get 1 divided by this, which is going to be the exponent times -1 plus 1, if that makes sense. So if n,
yeah, it does,
right?
Because it's in the denominator and the integral.
And then you'll always get this. This will always come out if you do this method. The exception is if P times V is constant, right? So here, if you have PV is right, which is something someone asked, right? So now P is equal to C over V. So when you integrate 1 over V dV, then you get, this is the natural log of V.
Yeah, that was on the homework.
Right? So, another thing, I think this is because I'm Canadian. Sometimes I'll call the natural log ln. That's something that sometimes people ask me what the heck I'm talking about. So if I ever say lawn, like I'm not talking about my grass, I mean the natural log. So those are both really good questions. So now what we can do is, now that we've got an expression for work, right? And then so here, this was just saying this is all the same stuff. So if you go on the slides or you watch the video when I post the video I've already posted, we did the same process, right? So we get to this same symbolic solution. We see that we didn't have V2. So we just use the fact that we know P1 V1 to the 1.2. You could do this to find the numerical value of C, but you don't ever actually need the numerical value of C, right? So as we work through this, right, we can get to the same expression that we have, but we don't know V2. So here we can see that I can get an expression for V2. So I could find C as an intermediate step, but that would take me a little bit of extra time. So here I just went right through. And again, the nice thing about keeping this as a ratio here of P1 divided by P, this should be P1 divided by P2, is that this ratio here, as long as my units are the same, it's going to drop out. So I converted, when we were doing it by hand, all this stuff to kilopascals just because I think that's safer. But even if I didn't, it wouldn't have mattered as I'm calculating V2 here. So we can put stuff into our calculator and we see that V2 is 0.136 meters cubed. So now we know V2. So here, the good thing too, we can see that V2 over here, right, is less than V1. And we know that from our picture, right, because we showed that we were compressing our system. So that's good that the volume is getting smaller, because that's what we think, that as the volume gets smaller, the pressure gets bigger. So I don't know if the numbers are right, but conceptually I know they're moving in the right direction. So here, if I want, I can remember here that kilopascals are really kilonewtons per meter squared. So then this kilopascals becomes 340 kilonewtons per meter squared multiplied by something times meters cubed. So when I do that, the meters squared drop out and I cancel out, this exponent becomes 1. So now I have kilonewton meters in both of these terms down here. So I'm getting the right unit, right? Because a Newton meter is a joule, so that's kilojoules for work. So my heat transfer was also in kilojoules, so this is encouraging. Now, I get that the work is negative. Does that make sense? So we know that in order for this process to happen, we're pushing our cylinder in, right, to make the volume smaller and increase the pressure. So that's work being done on the system, or we're adding work into the system. So this is work in. So we know that work in is negative. So it does make sense that this work term is negative. So you can see that any time in a closed system, if our volume is getting smaller, we're compressing something, we should be doing work on our system. So here work in is negative. And that physically tells us that the surroundings are doing work by compressing the system. So now we go back to our equation. We know our work. We know our heat transfer. We talked about the magnitude of the heat transfer being 2.2 kilojoules, but that's heat transfer from the gas. So this is heat out because the gas is our system. So Q is negative 2.2 kilojoules. So when I put that into my system, right, I get that U2 minus U1 is 74.4 kilojoules. And if the problem only asked me for the change in internal energy, then I would be finished. But it asked me for the change in specific internal energy, right? So here I guess we can also ask, does this numerically make sense? So we had heat that was leaving, that's negative. We have work that's also negative, right? But this is negative of a negative, right? So it becomes positive. So what this means is that the work that's going into the system is bigger than the heat transfer that's leaving the system. So on net, we're storing energy in our system, right? And that you could imagine that makes sense because we are compressing it so much. So we're definitely trying to store energy in this gas by increasing its pressure. So the problem actually asks us, and I didn't do it here, right? So I don't have the numerical answer in front of me. But here, right, so the problem is actually asking us for the change in the specific internal energy, right? So here I know that this would be the mass times U2 minus U1. And that's going to be equal to 74.4 kilojoules. So then U2 minus U1 is going to be equal to 74.4 kilojoules divided by, if I go back up to the problem statement, I can see how much mass we had. So 0.183 kilograms. Oops. I don't know if anybody has a calculator here. I got one on my desk somewhere. So if I take 74.4 and I divide that by 0.183, I get 406.6 kilojoules per kilogram. So this is nice because I get a unit that is in the right units. So it asks me for change in specific internal energy. So energy is in kilojoules, and anytime you put specific in something, it means per unit mass. So I'm getting an energy per unit mass, which does make sense. So that's how we do this problem. Does anyone have questions about the problem that we did here in class? Well, if not, you're certainly free to go. If you'd like to stick around, if you have questions about the homework or anything, you're welcome to do that as well. And if you have questions, you can just let me know, and we'll start to work on them.
Yeah, I got a couple of questions about the homework.
Shoot.
Okay, so first I was kind of wondering what section of the process should we actually do the computations themselves in?
My advice is always going to be do the numbers last. So do as much of the symbolic solution early. So keep the variables written until the very end, and then add the numbers at the end. So the reason I like to do that is, first, we might see little tricks, just like we did here, right? When we started to do this integral, that this just becomes P1, V1, and then we get this idea that this happens every single time. Second, it makes it easier for you to go back and see what you did, but also makes it easier for someone else to grade.
Okay, that makes sense. Oh, and I also have another real quick question about where do we find the week 1 lecture?
Oh, the one I need to post that still. So I think that I made it. I think that I didn't process it in YouTube and put it up. So the version of it that was not live should be available here, right? So if you go into week 1, it's here, lecture 4. But thank you for reminding me. I think that I have not posted this yet. So I'll do that after class. I'll do this one. It takes probably about an hour or so to process. And then I'll post a link. So I have not posted the live version of the lecture here. But you should be able to find it here in week 1. So I'll do that right after class.
Okay. And one more thing. So you post the solutions about the homework. Should we use those kind of as a guide, or if we get stumped, or just to check?
So I think that it's good to use them at the end. So again, my encouragement would be, so we do this in heat transfer too. So you'll see it later on in the course or in the curriculum. But I think the first step should always be to do it by yourself without looking at answers or homework. This is true for any class. Don't spare yourself the struggle, because the struggle is kind of when you learn. So, I mean, there's nothing stopping you from just going and looking at the solutions and writing them down. But I think you'll learn better if you struggle with it for a little bit, right? Or you try it, and if it doesn't work, then kind of look at solutions, or, work in a study group or something. I realize that might be harder now than it had been in the past. But my advice would be to go to the solutions after you've made kind of an honest effort yourself and either got to an answer, you want to see what it's right, or you got stuck and you can't figure out what to do.
Okay, sounds good.
Are there any other questions about the homework or the course or anything else? It's maybe a little broad.
Mine doesn't have to do with the course or anything, but I just realized that I didn't hand in the academic honesty thing. So is there any way
I think it's fine. There's no grade associated with that, so I think that
okay.
Part of that is an exercise to become familiar with kind of scanning things and submitting them to a Dropbox. So there'll be no academic penalty for not submitting the form.
Okay, thank you.
You're welcome. Well, if there are no further questions, you're certainly free to go. I mean, you're always free to go, really. But I have nothing more to share with you. But if you'd like to stick around and ask other questions, I'll certainly be here until we have no further questions.
Yeah, I have a few questions about the quiz. Should I wait until after the quiz is due to ask them?
Yeah, that might be better, just because there are people that haven't finished the quiz, and I wouldn't want to give people sort of maybe a heads up on that kind of stuff. But if you like, you can send an email too if you think that there are answers that or questions that that fit well in an email. But if not, maybe we can talk before tomorrow's class. Try to get less light right at my camera.
I also had a question for homework 0.
Yes?
Question 1.49.
Okay, so here if I go into content. Yeah, so what was the question? Oh, apparently it wants to load. Yeah, my internet connection is unstable.